Today we're going to be talking about definite integrals. So it's kind of weird. What I'm doing is I'm just going to talk about two different sections. The first one, we're basically just going to give an overview of. I just want to talk about what a definite integral is, but there is a lot of work to be done in 6.3, and it's not that it's not important, but you certainly don't need to be able to compute these sums by hand in order to evaluate definite integrals. But I do want you to see where definite integrals come from, and I want to talk about the Riemann sums briefly. So we're going to go through a little bit of the 6.3 notes and then move on to 6.4, and they all tie together. So I'm just going to do this all at once, and we'll see how it goes. All right, so 6.3 is talking about area and the definite integral. So far, we defined an indefinite integral in section 6.1. And today we're going to talk about a definite integral. So imagine that you have this curve, f of x, and we're going to be looking at what's happening underneath this curve from x equals a to x equals b. Now, the whole idea here is that if I wanted to approximate the area under this curve, at this point, all we would really know how to do would be to approximate it, because I don't have a formula that can get me the area underneath here. So like back when you were in geometry, you talked about areas of squares and rectangles and trapezoids and circles and all kinds of different polygons. But in this case, we don't have that situation. You've got this very fluid curve. And if I was trying to talk about the area under the curve, all I could do is just approximate it. So the idea here is we could look at different curves, and I could approximate the area underneath the curve by putting some rectangles of equal, really any sort of rectangles you want. In this case, we have rectangles of equal width and just varying heights, and we could just sort of line them up so that the left endpoints are sitting on the curve. And now some of these rectangles would overshoot the area. So like, for instance, here you have some rectangles covering a place where you don't have area under the curve. And again, this one's above. But then on something like this first rectangle, it's not covering the whole area because you have space below. So it's an approximation, but it sort of gives you an idea if that's all you're looking for. You could do the same thing, but with right endpoints. So in this case, you're taking the rectangle and you're lining up the right endpoint of the rectangle with the curve. And again, you're sort of overshooting it in some places. This one clearly is just going to include more area than you need, but then you're not including some of the area under the curve here and here in the second and third rectangles. So this is the idea for how to find the definite integral. So the whole idea behind the definite integral is we're trying to figure out what is the exact area under the curve. Now, the idea is, as you kind of work your way through these notes, there's a lot. There's honestly just really beautiful notes. Professor Sugar made these. The pictures are awesome, but we're just not going to have time to go through it all, but that's fine. Okay, so the idea is if I were to take these rectangles and I look at the area, maybe using the left points, using the right end points, and then maybe even talking about the midpoint. So in this case, lining up the midpoint of each rectangle underneath the curve, and then just seeing how those areas are similar is like something you would do in 6.3. And then a whole lot more that you would do that we're not going to do. And then what I really like is this graphic here. It's on page 14 in your notes. So you're given an example of this curve, and you're seeing it again and again and again in different situations. So in the first example, you're getting the rectangles such that the left point is lining up underneath the curve. And then you're seeing the same with the right endpoint in the second example. But both times you're seeing 4 rectangles. The idea behind the definite integral is that we can split those rectangles up so that their widths are smaller and include rectangles. The idea is the more rectangles you put under the curve, the closer you're going to get to being able to approximate the area under the curve. I know the area of a rectangle, so as long as I can add up these little areas of the rectangles, I can get a good approximation. Now, again, the way that you line these up is going to dictate, depending on the curve, if you're undershooting the area or overshooting it. But the more and more rectangles you get, the less of these errors you're getting. And you're going to see some more pictures of the same curve, now splitting this up into more and more and more rectangles. So in this case, when it says partitions, that's just talking about how many splits you have. So we've partitioned this one into 32 different rectangles. And then again, it gets split up again. So each one of those rectangles gets split in half. And the more and more and more rectangles you get, the more and more and more closely you can approximate the area under the curve. So that's the whole idea. This gets really complicated though, because there are lots of formulas you have to use in order to be able to approximate these sums. And it gets tricky. If you're really interested in seeing this, please feel free to stop by the office hour and I'll be happy to go over it with you. But let me tell you what the whole key to all of this is. The area under the graph of f is equal to this limit, which we're not going to be doing because it talks about all these partitions, which are not important, but it's not something that we're going to be spending time on. But what I do want to talk about is this idea of the definite integral. Okay, so the definite integral looks like this. It goes from a to b. I'm going to write this in English words for you so that you know what this is stating. But basically, it just says the integral from x equals a to x equals b of f of x dx. So this is a definite integral. So far, we've only talked about indefinite integrals. Indefinite integrals don't have these lower and upper limits of integration. But for the definite integrals, we have a lower limit of integration and an upper. And these are just x equals values because they correspond to the variable of integration that you have inside the integral. So this is a definite integral. We use it to find area under a curve. That's the main application, but you'll see there are other applications as well, which we'll talk about a little bit later today. As far as the area under a curve, I thought it would be helpful to look at this example that comes next. Okay, so here's the geometric interpretation. If you're talking about the integral from a to b of f of x dx, what we're talking about is this gray area, this shaded area. So you're going from x equals a to x equals b. Those are your cutoffs. And the area is just covering this space underneath the curve. Now, in the second example, the area is actually negative value. And the reason for this is because the y values are negative. So sometimes when you're computing area, I know you've talked so much previously in geometry about how certain quantities could be negative. And one of those was like area and distance. And in this case, area can be negative because the y values are negative. You're going to see some more of this in later sections. But in this case, we would say that the area can be negative because the y values are negative. And it just is what it is. Now, what that means is that I'm going to give you a different scenario here. I'm going to try to make this look as good as I possibly can. But imagine that you had a curve that looked something like this, and you were asked to find the area under the curve from A to B. Well, imagine that A is, in this case, sitting at the origin, and then we have this chopped off at B. So the idea is that the area above the x-axis and the area below the x-axis, I tried to make them look exactly the same. I tried to make this look symmetric about the middle, but the area would actually be 0 in this case. And if you're wondering, like, how can that be? Clearly there's space under the curve. It doesn't matter because the space above the curve is going to be positive area, and then underneath, or the space underneath the curve from A to this middle point will be positive area, but then we have that same exact amount of negative area that's counteracting that underneath the x-axis. So over here we would have positive area, negative area. So we would say that the area is 0 because the area above equals the absolute value of the area below. So those two would be the same. Okay, so they would sort of like cancel each other out. Now putting it all together, you have something like this. Now notice that the shaded region above the x-axis is shaded in yellow. That represents positive area. And then what's shaded in green below the x-axis is negative area. So the idea here is if we're to put this all together into a definite integral from a to b, f of x dx, what we would be doing would be adding up some regions and then subtracting off other regions. We've already used A, B, so let's call some of these regions, and we'll just label them. Let's say we have the first yellow region is C. First green region would be D. And we'll go E, F, and G. So in order to find the area under the curve, what I would be doing would be adding up all the areas that are above the x-axis. So I'd be taking C plus E plus G. So this is the area above the x-axis. And then I'd be taking off the area below the x-axis. So anything down there will subtract some of those areas. Oh, let's see, that would be D. Would you believe that I forgot my whiteout again? I might as well just throw in the towel at this point. Okay. D and F. So much whiteout in this house. I got like a billion pens and no whiteout. Ah. Okay, this would be the area below the x-axis. All right, so that's D plus F. All right, so that's the idea. We're going to apply this to another example, and then we're going to talk about like how would we actually zero in on what these actual values for the area are. So we're going to do that in 6.4. The last thing I wanted to show you in 6.3 is this example. So you are going to consider this graph. It's y equals x squared minus x minus 2 from x equals -2 to x equals 3. And we're being asked a couple questions. Now, what I like about this particular example is you sort of have to interpret what the symbols are saying, and you got to get used to thinking about calculus in this way at this point. So the first question is asking you, what is the area under the curve from -2 to -1? So we're really just following these limits of integration, the lower limit of integration and the upper limit, to figure out where we're going from left to right on our curve. And what we're going to be doing right now is just approximating the area, because that's all we can do until 6.4. So I'm going to look from -2 to -1. So that would cover this region. And I'm going to ask myself, like, approximately what is this area? So if I was trying to eyeball this, I'd be like, I don't know, like, let's say maybe I took this portion up here and like I placed it down there. That would give me like about 1 unit. And then let's say that I took this portion here and placed it down there. Those two would add up to be like about another unit, maybe a little bit less. So I could say that the area from -2 to -1 underneath this curve would be about 2 square units. So I'm counting the squares here. Back to how you originally talked about area back in the day. Okay, now we'll do the same thing, but this time going from -1 to 2. So if I'm looking at the area from x equals -1 to x equals 2, I'm talking about this region. Okay. So from -1 to 2, again, I'm just going to count some squares. Now, we have a full square right here, so we have at least one. And then you can just start like adding up the pieces that you think go together. So I would say like this portion, even if you tagged on this portion of a square over here, you probably have a little bit extra left over. Same idea here. I could take this piece right here and sort of try to fill it in there. I'd have a little bit extra. And then I still have this square here in the middle, and then this little piece on the bottom. So I also need to consider the fact that this area is occurring underneath the x-axis, the whole thing. And that's why this was split up this way. So you can see area above and area below. So when I approximate this area, I need to make it negative, and I need to just try to add up the squares just to estimate. So my estimation is I have about 1, 2, 3, 4, maybe add in another half for the excess. So it's approximate to the best you can, but I'd say it's like about -4.5. If you said -5, I mean, it's an approximation. You do the best you can. The last chunk of this is talking about the region from 2 to 3. And again, that's covering area that's above the x-axis. So this would be the region right here from 2 to 3. So looking at that, I'm just looking at the area in here, and this looks symmetric to me, and I guessed that it was about 2 for the region between -2 and -1. So I'm going to say about probably the same. It's positive because it's above the x-axis. So that's my estimate. So the whole idea here is we're trying to really find the area from -2 to +3. So what I'm going to do is I'm going to put these pieces together to get an approximation for what we think the area would have to be. All right, so I'm going to add up here all the components. I have 2 minus 4.5 plus another 2. So 2 and 2 is 4. Minus 4.5 is about -0.5. I should make these approximately equal signs. But that's what we're guessing the area would be. Now, again, if this bothers you because you're like, clearly area is going to be more than -0.5, you cannot keep thinking about the way that you used to think about it. We have to start thinking about area as being positive above the x-axis, negative below. And if the area is -0.5, that means that you have more area that's underneath the x-axis than is above the x-axis. So we're going to look at this exact same example in the next section in 6.4, and we're going to figure out if our approximation was good or how close it was and see. So that's what I had to say about 6.3. Like I said, there's not a lot that I wanted to do there except just basically give you an introduction into definite integrals and, of course, give you that notation which occurs in 6.3. All right, so 6.4, we're going to talk about the fundamental theorem of calculus. If something is called the fundamental theorem of calculus, that means it's important, especially with the class you're taking is called calculus. So this is the fundamental theorem. It's a really big deal. So pay attention. Our objectives are that we're going to find areas and evaluate definite integrals. So sometimes you'll be asked to find an area, and sometimes you'll just be asked, like, here, evaluate this. Either way, we're going to get some practice evaluating. Then we'll be doing this using the fundamental theorem of calculus. So it's very cool. I am going to a lot of times refer to this as the FTC. So I don't want you to be like, what is she talking about, FTC, fundamental theorem of calculus? It's just a mouthful, so I like to say FTC. It's funny because I can say to my L3 students, like, all right, now we're going to use the FTC, and be like, what are we doing? But they know the process. They just don't know that it's called the fundamental theorem of calculus. All right, so far we don't have a nice way to find definite integrals because we had to compute a bunch of crazy sums in 6.3 that we decided we were going to do. It's crazy. Until now, all we knew was a definite integral was defined to give us area under a curve. The FTC is going to connect the area problem and the definite integral with the indefinite integral from 6.1 and 6.2. So here's the FTC in all of its glory. The fundamental theorem of calculus. Let f of x be a continuous function. You can draw the whole thing without ever lifting your pencil on the closed interval from a to b. Then the integral from a to b of f of x dx is, we're going to find the antiderivative, capital F, and we're going to evaluate that from x equals a, x equals b. This is usually the notation shown for when you're evaluating. You just put this vertical line sort of on the end, and then you say, all right, I'm going to go from here to here. And then what you're doing when you evaluate it from a to b is you're taking that antiderivative and you're first evaluating it at b. So everywhere you see x, you swap it out with b. And then you subtract off the antiderivative evaluated at a. So everywhere you see x, swap it out for a. So you're just evaluating the antiderivative at b and a, and then taking the difference of those two. So it's very cool. I'll show you some shortcuts for how to do this in your calculator, but please make sure you're showing all of your work on your test. Okay, so I'm going to go through some examples, and I think this will, I think you'll pick it up pretty quickly. Another thing is this section is great because it helps you review some of those concepts from 6.1 that you maybe haven't seen in a week. So really good stuff here. Now, if this integral from -2 to 3 of x squared minus x minus 2 dx looks familiar to you, it's because it's that same integral that you saw in that last problem we did where we estimated the area in 6.3. So we were looking at x squared minus x minus 2 from x equals -2 to x equals 3. So what we're going to do now is actually find the value of the definite integral, and then we'll compare it to the estimate that we found, and we'll see if we get close. Remember, the estimate we found was -0.5. So, I'm on pins and needles. I don't know what's going to happen. Yes, I do, but I still feel like the suspense is part of the fun here. It's part of it. So what I'm going to do first is I'm going to take the antiderivative, and then I'm going to evaluate it from -2 to 3. So to do this, I'm going to integrate. I'm going to add 1 to the exponent and divide by the new exponent, and I'm going to do that for each term. For x, I'm going to make this 1/2 x squared, and then for 2, remember we're just popping the x onto the constant. And the way that I show this is I'm just going to have that vertical bar, and I'm going to go from -2 to 3. You don't have to write the x equals, but please do so if you find that it's helpful. All right, so now I'm going to first evaluate at 3, and I'm going to subtract off what happens at -2. You can do this term if you want, but usually what I do is I take the whole thing and I evaluate it at the upper limit, then I subtract off the whole thing at the lower limit. So we have 1/3 times 3 cubed minus 1/2 times 3 squared minus 2 times 3. And I make brackets my best friend here because I need to make sure that when I subtract off the lower limit, that I'm taking off every single term using subtraction. This is one of the things that students will mess up most often because they're careless with distributing in their negative signs. So let's be super careful here. And there are a lot of negative signs to deal with in this one because the lower limit's negative. Okay, so now I'm evaluating that whole expression at -2. I'm just going to simplify and then do some arithmetic. I mean, at this point, this is just like an algebra 1 order of operations problem. So I'm going to go ahead and evaluate and simplify. So 3 cubed is 27, divided by 3 is 9. 3 squared is 9, so we have 9 halves, and then minus 6. Now, when I go through and I evaluate the lower limit, I'm going to make sure I distribute this negative sign into all 3 terms. That's going to throw off your area if you forget to do that. Don't forget it. I'll keep reminding you. Okay, so I have minus, And then I have negative 2 to the third, which is negative 8 divided by 3. So negative 8 thirds. So it's minus a negative. Be careful there. Negative 2 squared is 4. Divided by 2 is 2. And I have minus a negative, so I have plus 2. I know, signs. Oh, always the signs. Negative 2 times negative 2 is positive 4. Distribute negative, and you get negative 4. And then you're just going to add these up or subtract them, whatever you have to do. Okay. Oh, look at, I mean, see, if you need a reminder about how far we've come, just look what we were doing last time. Would you rather be doing this? No, you'd rather be doing this, right? So be happy. At least we're not doing that. Just my 2 cents. 9 minus 9 halves minus 6 plus 8 thirds plus 2 minus 4. All right, so I have this fraction, or I have this decimal. Remember, I want exact answers. So you're going to hit the math button, enter, and give me a fraction. We got negative 5/6. That's what I want to see. Now, remember, your estimate from 6/3 was negative a half. So, I mean, it wasn't terribly off. It wasn't as close as we would have liked. We should remember I said that you could have made this like negative 5 and it would be a little bit closer. If we had done that, we'd get negative 1 instead of negative a half, which maybe would have gotten closer. But it doesn't matter. It was just an estimate. We're eyeballing it. It's close enough. I mean, if your real answer was like negative 3 and you estimated it at like negative a half, then I'd be like, yeah, your estimate's really off. But I don't think that's that off. I think you're okay. Okay. Use the given graph to interpret your answer geometrically. So this is something we did in 6.3, but I mean, basically the idea is just that this integral from negative 2 to 3 of our function is just going to be equal to, you have a sub 1 and a sub 3 above the x-axis. So a sub 1 plus a sub 3, and then you're taking away the area that's below. So same idea as what we talked about in 6.3. Whoops, sorry. You can see that on your paper, but okay. One thing I did want to mention, because I told you I'd show you an easier way to check this in your calculator. There are a few different ways, and some of them are like almost like cheats because they're like too easy. So I'm going to show you a way that I know will work on everyone's calculator. The idea is I can take my antiderivative, and if I'm trying to evaluate it, like let's say you're kind of like, whoa, this is a lot of negative signs and a lot of like negative numbers, and I don't know if this answer is right. What you can do is you can evaluate this in your calculator a little bit faster. Maybe not faster, but at least you wouldn't be so worried about exactly all these negatives. So I'm going to put this antiderivative into my y equals menu. So this is 1/3 x to the third power minus 1/2 x squared minus 2x. Now that's the antiderivative, that's not the original, because I'm evaluating the antiderivative from a to b, not the original. Okay, so what I'm going to do now, this is saved in my y sub 1. I think we talked about this for limits, but it's been a while. So what I'm going to do now is I'm going to go to my variables button, ARS, and I'm going to scroll to the right to y variables, and then I'm going to enter a function because my function is a function. And I put my function into y sub 1, remember? Okay. So what I'm going to do is I'm going to pull up my y sub 1. Now this is the same y sub 1 that I've entered. Okay, take my y sub 1. I'm going to open up a parenthesis right here. And I'm going to take y sub 1 and I'm going to evaluate it at b, which for us is 3. Close your parenthesis, and then I'm going to pull up my y sub 1 again. So I'm going to say minus variables, scroll to the right, y variables, enter for a function, enter for y sub 1, open a parenthesis. My lower limit is -2. So I'm going to take my antiderivative, which is my y sub 1, and I'm going to evaluate it first at 3 and subtract off the evaluation of the antiderivative at -2. And then I better get -5/6. I do. I mean, it's the same decimal approximation, math enter, -5/6. So if you want to check this in your calculator, that's fine. I do want to see your work, but please make sure that if you're not 100% sure about your answer, you're checking it in your calculator. And if you get a different answer, go back and look at your work and see what happened. I just want to give you a way to sort of feel more confident about your answers. And hopefully you don't enter it in your calculator wrong and second guess your work. That would be terrible. Okay. So that's how we use the FDC. We're going to just be using that a couple of times here with some integrals that we already know how to deal with, but this time definite integrals. So on to the next page, I'll give you some examples. Now we're just going to be evaluating definite integrals here. We're not pulling this area application back in yet. Number 1. Oh, you know what? I was going to say one more thing. Note. There is no plus c on definite integrals. So I made a big deal in 6.1 and 6.2 about putting the plus c on your integral. You don't need that. You're not supposed to have that in 6.4 because we're not saying like we could be adding other quantities in. We're not doing that. We have an absolute definite answer in this case. It's a number, not a function. So there's no plus c. Your definite integral is just a number. Okay. So when we go back to indefinite integrals, I'm going to have to remind you to put your plus c back on again because you got into the habit. Such is life. All right, so example 1. This one is going to be the integral from 0 to 2. And if you're wondering, by the way, I'm going to have 3 examples on this page, so you can kind of space that out accordingly. This one is going to be 2x cubed dx. So very basic integral to start out with. So the first thing we're going to do is we're just going to take the antiderivative. I'm going to increase the exponent by 1 and divide by the new exponent. And then I'm going to evaluate that from 0 to 2. Okay, so that's the way that we're going to look at this. Now, if you just have a constant multiple, which in this case simplifies to a half, it's kind of up to you if you want to keep the 1/2 on your x or if you want to factor it out. I tend to say let's factor it out, but it's up to you. So if I do that, now I'm taking 2 to the 4th minus 0 to the 4th when I apply the FTC. And then I simplify. So the 2 over 4 gave me the 1/2. Then x to the 4th is what I was taking from 0 to 2. So starting with that upper limit and then subtracting off the lower limit to the 4th power. So it's 1/2 times 16, which is 8. I'm going to show you another way to check this in your calculator, however. It's not always going to be as easy as this. Some of these will be a little bit harder to check. It kind of depends on what the curve looks like and what the limits of integration are. But let's say I'm looking at this function and it is 2x cubed. Earlier I said put the antiderivative in your y equals, but the way that we're going to check it using the graph is to use the original function. So I'm going to ask my calculator to find the area under the curve, this curve. I'm going to zoom 6. Okay, now what I'm looking for is the area from 0 to 2. My calculator might struggle with this because I think that when you have, for instance, if you're not sure, look at your table, and x is 2, y is 16. If it's not in the window, I think it struggles to find the area. But what I'm going to do is I'm going to go to the graph and I'm going to hit second trace, which is calculate. And I'm going to ask it to find the integral for me, which is 7. Or you can just enter 7. And it's going to ask you for a lower limit. The lower limit is 0. So it's already at 0. So I'm just going to say enter. And it's going to ask you for upper limit. My upper limit's 2. So I'm going to type 2. And then I'm going to hit enter. And it does indeed give you the area under the curve as 8. So it will find the integral for you. You can, of course, use that. The difference, the times when this would not be quite as helpful would be like, let's say, if I was going from, oh gosh, now I can't remember what your calculator does. Let's say I had a lower limit of -2 instead of 0. And my upper limit was +2. Oh, no, it does do that. Oh, you know what I'm thinking about is area between curves. This gets trickier. But yeah, notice how I changed my lower limit to -2 and then I went up to +2 because of the origin symmetry here. I ended up getting an area of 0 because the area was the same. But the absolute values of the area was the same on the above and below the x-axis. So anyway, interesting. So this is a way that you would check that in your calculator using calculate number 7. There's that. Number 2. This one is the integral from -1 to 2 of x squared minus 2 quantity squared dx. I really like this problem. And the reason I like it a lot is because students tend to always start out wrong on this one. So why would I like that? Because I feel like it makes it really instructive to actually go through the solution process. So you know what I see students do? Anytime students see something that looks like a composite function, here's what they do. They're like, oh, well, let's try letting u be x squared minus 2. And they think like that's a good idea because I see parenthesis and I see quantities being squared. But if you did that, your du is 2x dx. Now, it's not the end of the world that you can get rid of this 2, but what about the x? X dx. Do you have an x dx? No. And if you're like, what are you talking about? I could just rewrite this. Like, this would just be u squared. Okay, fine. U squared 1/2 du is x dx. How would you sub this out? You can't get. What if you try to do this 1/2? It's almost painful to do. It'd be like, oh, okay, I have u squared dx then would be 1/2x du. Oh. And then you're kind of like, I don't know. And then you'd run into some problems. So this is messy. This is a big no. Okay. No. Two exclamation points. Do that. The u substitution won't work. This is the tricky thing about integration. It's not, you cannot just like force your way through an integral. It has to fit a specific form. In order to do a u substitution, you have to be able to either see the derivative sitting inside there somewhere or be able to recreate it easily. And in this case, there's nothing that you could do about that. You took you took the du, you divided by 2, and you're like, all right, it's x dx. Then you divided out the x, fine. And now what? You're stuck. So don't do that. because now you have u's and x's in the same integral together, and you'd have to back sub the x, and you'd end up with something that you don't know how to integrate. All right, so don't do that. Now that we've talked about what not to do, let's talk about what you would do. This is from 6.1. So if you can't do the u substitution, then simplify the integrand. It's just a matter of just doing a little bit of algebra on it. Whatever you do, oh, here's another, oh, you know that this is my thing here. I've chosen this hill to die on. Don't do that. You cannot distribute the exponent into this sum or difference, in this case difference. Okay, don't do that. This is also like a no. I know, all these things I don't want you to do. What do I actually want you to do? I want you to take x squared minus 2 and multiply it by itself. That's what you do when you square a quantity. You multiply it by itself. All right, so now that we have that, you can simplify. So turn this into a situation where you would just be able to use that power rule for integration. So this will be x to the 4th minus 2x squared for the outsides, minus 2x squared for the inside. So that's minus 4x squared. And then the last terms give you plus 4. So it's close, but you're missing that quadratic term in the middle if you forget to FOIL. All right, so now we have this rewritten so that we can take the antiderivative. Once we take the antiderivative, then we can apply the FTC to evaluate the definite integral. So we have 1/5 x to the 5th minus 4/3 x cubed plus 4x. I'm going to take that whole thing from -1 to 2. All right. Let's evaluate it. If you want to put it in your calculator, that's fine. I feel like at this point, like there's a decent amount of work, but you know I'm stubborn and I just want to evaluate this. All right, so 2 to the 5th is 32. 2 cubed is 8. 4 times 2 is also 8. All right, so I'm going to use my brackets here. I'm going to subtract off what's happening at the lower limit. -1 to the 5th is -1. So that gives me -1/5 here. -1 cubed is still -1 times -4/3 is +4/3. And then I'll have -4. And now I'm just going to simplify. Usually at this step, I just start to put things into my calculator because it just turns into a lot of fractions. And like it's just a lot of work by hand that I don't need to do. So I usually kind of evaluate both of these, and then I use my calculator to simplify the expression. So I have 32/5 minus 32/3 plus 8. And then when I put this in my calculator, I'm going to distribute the negative sign as I enter these quantities. So instead of saying minus -1/5, I'll just say +1/5, and then minus 4/3 and plus 4. Sometimes I even think about it as I'm just going to switch the signs on all of those lower limits. Math, enter, enter, and you get 33/5. Now, technically 6.6 is an exact answer. It's not like you have to round it. So 6.6 would be okay in this situation. In general, I'd like for you to get into the habit of writing these as fractions. So this one is 33/5. Okay. Number 3. I'm going to take myself to the Target and get more colors. I'm finding myself getting bored with these colors. Who would have thought? The Target. All right. We're going to go from 1 to 4. In the numerator, I have 3x cubed minus 2x squared plus 4. In the denominator, I have x squared dx. So I'm integrating this entire fraction. And again, this is a situation where I'm going to take you back to 6.1. So there's not a substitution that you would do for this, but you can use the fact that your denominator is a monomial, one term, to simplify this integral. So really what you're looking at here is 3x cubed over the common denominator minus 2x squared over the common denominator plus 4 over the common denominator dx. So this is a technique that we talked about even when we were simplifying expressions to take derivatives. When we took the derivative of this, we split it up the exact same way, just using the common denominator, separating fractions. So at one point they were put together, we're pulling them back apart. And then we'll just rewrite this. X cubed over x squared is just x to the first. So we have 3x minus 2, your x squareds cancel out in the second term, and then plus 4x to the negative second power dx. Okay, now that we have this written in a nice, easy to use form, we'll just go ahead and integrate or find the antiderivative, and then we'll use the FDC to evaluate. All right, so I have 3 halves x squared minus 2x. This term, when I increase the exponent by 1, I go up to x to the negative first. When I divide by negative 1, I'm taking 4 over negative 1, which is making this term negative. So this is what my integral will look like, or my antiderivative. And this whole thing is getting evaluated from 1 to 4. So I'm going to evaluate at the upper limit and then subtract off what's happening at the lower limit. So we have 3 halves times 4 squared, which is 16, minus 2 times 4 is 8, minus 4 over 4 is 1. This whole thing, and then we're going to take off, we're going to subtract the integral evaluated at 1, or the antiderivative at 1. All right, so 1 squared is 1. 2 times 1 is still 2. It's still just a negative there. And 4 over 1 is 4. And this is another spot where I'm going to stop and just put this into my calculator. And again, when I put this into my calculator, I'm going to just automatically distribute this minus sign into the parentheses. So I have, you do what you want here. I'm just going to take 48 divided by 2, which is 24, or you could just take 3 times 8. Either way, it's 24 minus 8 minus 1 minus 3 halves plus 2 plus 4, and I come up with 19.5, which is exact, also known as 39 halves. Let it be. You can always check this in your calculator if you don't feel comfortable with your math. Okay, let's do another one. This one is going to have an A and what example am I on? I think I'm on, sorry, you know what? I renumbered these and I'm all like discombobulated. I was on 1. Why did I do that? I'm on example 4. We'll call this 4A. Right. 4A. So this is the integral from 1 to 5 of 2x minus 1 over x plus 1 dx. All right, so let's go ahead and find the antiderivative. Now this one, remember, is your natural log of the absolute value of x here for this middle term. So I'm going to integrate that as such. Remember that 2x is the derivative for x squared. And then the integral, or the antiderivative of 1 dx is x. All right, so I'm going to take my antiderivative and go from 1 to 5. I'm going to start out evaluating this one at 5. So this will be 25 minus the natural log of 5. And because 5 is positive, you can drop those bars. and then plus 5, minus 1 minus ln 1 plus 1. If you would like, you can just change the signs and you won't have to worry about the second set of parentheses. I like to keep it though. Old habits die hard. So just keep on keeping on. The natural log of 1 is 0. Hopefully we're used to seeing that from the last chapter. Okay, now let's simplify. I'm just going to go ahead and add up all the like terms. So ln 5, I can't add that into anything else, but I can add up all the other terms. So I have 30 minus, and then 1 plus 1 is 2. So 30 minus 2, and then minus ln 5 is going to be 28 minus ln 5. This is exact. You could, of course, get a decimal approximation for this and approximate it using the graph on your calculator. But this is an exact answer. I want you to leave it exact. Okay. Now, the reason that I call this A is because there's a second part to this that we're going to call B. And they're going to look really similar. And I want to show you what the problem with B is. So B is going to go from -1 to 5, but we're going to take the integral of the same exact function. And if you're wondering, like, why would we do this? Well, I'm going to show you. I'm going to show you why. Let's see. First of all, I guess technically we could look at this antiderivative because everything would look like it's just fine for now. And you'd be like, yeah, what's the problem? I should just be able to evaluate this. No big deal. Well, let's look at this on the graph. 2x minus 1 over x plus 1. All right, so I'm going to graph it. I should be in standard zoom already. Okay. Now, if we looked at this from 1 to 5, I'm going to go to calculate. I'm going to go to number 7, lower limit 1, upper limit 5. Get this quantity. Now, it's 28 minus ln 5, so it's 26.39-ish. I mean, ln 5 is pretty small, so I would believe that's our decimal approximation. What happens if I do the same thing from -1 to 5? See how my calculator is kind of like, it's still thinking about it. Error. Tolerance not met. Calculation has reached the tolerance. Okay. That's because my calculator can't handle this. Do you know why? It's because the area is way too big for it to calculate. If I go back to my y equals, oh no, there we go. It's first of all, it still has this initial calculation in it. What it has to do is it has to go from x equals -1 all the way up to +5. When it goes from -1 to +5, it has to cross over a vertical asymptote. You can't do that with our definition of the FTC. Notice that when I gave you this definition back on the first page, let f of x be a continuous function on the closed interval from a to b. This function is not continuous at 0. Therefore, you can't actually find the value for the definite integral. Now, it's possible that you might try to do that, and you might say, okay, well, what's the problem here? I would have 25 minus ln 5 plus 5 minus, and then -1 squared plus ln absolute value of -1 minus -1, so +1. And everything seems like it should be okay, but you actually cannot do this. Now, I don't think you're going to see much on your homework where they're trying to trick you, but I want you to see that even though this looks like it's something that you can compute, you actually can't compute it. We cannot evaluate a definite integral over a discontinuity. And in our case, we have a vertical asymptote at x equals 0. Notice that 0 is not in the domain. And x equals 0 is inside this interval from -1 to 5. X equals 0 is in this interval. So we can't have that. It's bad for us. If you ever decide to take Calc 2, you will learn how to maybe evaluate those integrals, or maybe figure out that you can't evaluate them because they run off to infinity. But in this class, we're not talking about the case where we're evaluating a definite integral over a discontinuity. So we don't need to worry about that here. I just wanted you to just kind of get a sense for what it is that you're looking at here. You can't, if your limits of integration lead you to a situation where the function doesn't exist inside those limits, then that's a problem. The FTC only applies when your function is continuous on a closed interval from A to B. If there's a discontinuity, you can't do it. Okay, so that was why there's a part A and a part B here. For part A, even though there's a discontinuity at 0, you're not looking at that interval. You're just going from 1 to 5. So it doesn't matter. But here, you're trying to integrate over the discontinuity, and that's where you have the problem. All right. Example number 5. Find the area under the curve. Let's change colors. Example 5. Find the area under the curve. Find the area under of x equals 1 minus the cube root of x. And we're going to look at this on the closed interval from -8 to -1. Now, if you're thinking like, oh, she just tricked us, she's trying to trick us again, I see negative numbers and radicals. I'm not trying to trick you. You can take the cubed root of a negative number. You can take the odd root of a negative number. You just can't take the even root of a negative number. But we're okay here. I can take the cubed root of any number I want. The domain here is all real numbers. So I don't have a problem there. What I'm going to do is, and this is just this is worded differently so that you would just get a little practice setting up the integral. So far, I've just given you integrals. Now we're going to set them up. So this one is going from -8 to -1. So the left limit goes on the bottom. Right limit is that upper limit of integration. So from left to right means bottom to top. So from -8 to -1, and we're looking at 1 minus, and if it's the cube root of x, you can write that as x to the 1/3 power dx. Make your life easier. All right, now you'll integrate x minus, increase the exponent by 1, divide by the new exponent. So we're up to 4/3. We're multiplying by 3/4. And then we'll evaluate that from -8 to -1. Now, if you want to use your calculators, fine. I don't think you should need to, but you know what? It's fine. I'm going to evaluate this first at -1, and then I'm going to subtract off what's happening at -8. So there are a lot of negatives occurring here. So -8, and then -3/4 times -8 to 4/3. Oh, by the way, I sort of glossed over this, but -1 to the 4/3 is just -1. because, oh, let's see, you know what? -1, -1 to the 4/3. You know what? I should have written it as 4/3 because what you're doing here, it's not -1. It's going to be +1. You're taking it to the 4th and then you're cube rooting it. I'm glad I wrote that. What was I thinking? All right. That's fine. We'll simplify it. So this is -1 minus 3/4 times. I just put this in my calculator, but remember when you take something to a 4/3 power, the numerator is your exponent and the denominator is your index. So you're taking the cube root of -1 to the 4th power. -1 to the 4th is +1. When you cube root +1, you get +1 back. Okay, minus -8. I guess I could have distributed, but that's okay. Now, -8 to the 4/3, if you like, I know I feel like I'm giving just like a mini algebra lesson here. -8 to the 4/3 is -8 to the 1st times -8 to the 1/3. Remember that when you take, when you're multiplying with the same base, you add the exponents. So that if the base is -8, 1 and 1/3 will get me to 4/3. So we can turn this into -8 to the 1st, which is -8. And then -8 to the 1/3 is just the cube root of -8, which is -2. That's where that comes from. So I'm just trying to help you evaluate these without your calculator, because you know what? I've gotten so many quizzes from you all that have things written on them like, sorry, I forgot my calculator at home. If that happens, we need to be able to function with our calculators. All right, so -1 minus 3/4. I know, and I'm probably going to pop this into my calculator right now. We don't have to. I could just say this is -7/4, negative 4/4 minus 3/4 is -7/4. You know what? We're just gonna do this because I already made this big hoopla about like, well, what if you leave your calculator at home? So now it's just happening now. All right, +8. All right, negative, 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 negative. 4 negatives make a positive. Even number of negatives make a positive. And then I have 16 times 3/4. And you can put this in your calculator. I know. I don't know why I'm torturing everybody like this. It's because I made that statement about not needing your calculator. Now it's just happening. 8 is 32/4. 16 times 3 is 48. So you have 48/4. So now you just need to add up for yourself 32 and 48 and then subtract off 7. So my son's class, I know he's like 2nd grade, but they're learning about how you will add things by like taking away from a number and adding to another. They'd be like, oh, let's take the 2 from 32 and add it to 48 to get 50. And 50 plus 30 is 80. We'll probably do that. 80 minus 7 is 73. So we have 73/4. He was learning to borrow this morning before he left for school. I saw his homework. Like, did your teacher teach you how to borrow? Like, how does she expect you to subtract 3-digit numbers? Like, it didn't say borrow. It just, he was like, no, she didn't teach us this. I don't know what, these kids. I think the teachers just wanted them to like, I don't even know, but I had to teach them how to borrow at breakfast. Unbelievable. Now, since we were talking about area, you might want to say units squared, but you don't have to. Units squared. You can always check this in your graphing calculator should you choose to do so, but you certainly don't have to. All right, I have one more FTC example for you, and then we'll do an application problem. So, yay. I think I'm missing something. Did I miss something? I don't know. She's all over the place. I don't know. No. Did this, did that. Maybe there's an extra page. I don't know. 21, 22, 23. 2. All right. It's fine. Something has occurred with the pages, but everything is fine. Page 22. This one is going to be example 6, right? Between the page numbers and the example numbers, we're just all over the place today. Example 6. Okay, so this is another good one. I know they're all good, but some are better than others. The square root, and under the radical, you have 7x. And then, oh, that's not all. This is getting multiplied by the square root of x plus the square root of 7 dx. You know why I like this problem? It's because so many students forget how to work with these radicals. They're like, what can I do with these radicals? And I'm going to remind you now how to work with the radicals because it's such an important thing to know how to do. And I don't want you to struggle. I want you to be successful. Okay, so I think that when you look at this, you're probably thinking, I need to distribute. And you're absolutely right, you need to distribute. Gosh, I'm whacking things now. Okay, you do need to distribute, but if you distribute and you don't know how to simplify, then it's not helping you. So when we distribute, first of all, I need to take the square root of 7x and multiply it into the parentheses. I mean, how else would you do this problem? It's definitely not a u substitution problem. I don't even know how you would turn this into a u substitution. I've done a lot of crazy substitutions in my life. I want to remind you of this rule that says that you can take the square root of a times the square root of b. And if you're multiplying, you can multiply them under the same radical. Okay, so this is from algebra. Now, this does not work with addition or subtraction. So I'm going to make this, you know, I've written this out like 100 times in this class. The square root of a plus or minus the square root of b does not equal the square root of a plus or minus the square root of b. Okay, so that's not a rule. I mean, it's a rule that you can't do it. But this is like a no. No. Okay. But above, the square root of a times the square root of b equals the square root of a times b. That's a rule. Please use it. It works for products. It does not work for sums and differences. All right, so we have the rule. We're going to use it. So what that means is I'm going to rewrite this as the integral from 0 to 25. And I'm going to multiply these factors together under one radical. So this is going to become the square root of 7x times x, which is 7x squared. And then in the next term, I'm going to multiply the 7s, and I just have the x now. So this is going to be plus the square root of 49x. And be really careful with your radicals. Sometimes we write them a little too short, and then the quantities don't all get involved. And then, you know, we might think it's the square root of 49 times x. And then the x gets left outside. So be careful with that. And if you're like, wait a second, we can totally simplify this. Right. And we should totally simplify this. Don't leave it. So I can rewrite this again. The square root of x squared is x. So I'm going to write this as the square root of 7 times x plus 7 times the square root of x dx. I know so many things. So they look very similar, but they are not the same. But we multiplied them together. And if you would like, you can rewrite this one more time because I know you're dying to rewrite this one more time. So in this case, make sure the x stays out of the radical in the first term. So this is 7 times x to the 1/2 power. And I just thought it would be easier to rewrite it since we're going to have to integrate. If you want to have that written as a rational exponent. Okay, now we've done all this rewriting. Now we can take the antiderivative and evaluate that using the FTC. So let's do that. I'm going to increase the exponent by 1 and divide by the new exponent. The square root of 7 is just a constant multiple. It just hangs around. When I increase the exponent by 1 here, I'm increasing 3 halves. So I'm going to multiply by 2/3. And then x to the 3 halves. And then this quantity gets evaluated from 0 to 25. If you want to rewrite it first, I think that's going to be really helpful here. I know that you have your calculators, but one thing I like to do, and I think it's going to be really helpful to you in your entire math life, is when you see 3 halves power, x to the 3 halves is x times x to the 1 half, which is x times the square root of x. Now, you might not care about this when you're taking a derivative. You wouldn't want this. But when you're trying to simplify, you're going to find it's really helpful to you. So I'm going to rewrite this one more time before I use the FTC. I have the square root of 7 over 2 times x squared plus, and I have 14/3 x root x. And this is going to be especially helpful to me because I know I have a perfect square here, and I'm going to be able to evaluate that without my calculator. I know I keep telling you how to use your calculator because it's a really useful tool. But if you're one of those students who's like, oh my gosh, I left my calculator at home, I don't want you to be scrambling and like, I'm stuck. I have no idea where to go at this point. And this is so useful. So useful. All right, so here we are. We have the square root of 7 halves times 25 squared, which is 625, plus 14/3. And then we have times 25, and then the square root of 25. Now, the nice thing here is that with the zeros, both of these terms will zero out. That doesn't always happen with a lower limit of 0, but it will happen if you're looking at polynomial functions that all contain a variable term. All right, so now there's not like a whole ton I can do with this. 625 isn't even divisible by 2. So this is just going to be 625 halves times the square root of 7 plus, and you know, here's where I'm shooting myself in the foot because I made this big stink about not using your calculator, and now you're going to have to multiply this out by hand. Now we're back to like 5th grade math, and a lot of us don't remember 5th grade math, so I'm just going to put this into my calculator. 14 times 25 times 5. Is it divisible by 3? No. So this is going to be plus 14 times 25 times 5 is 1750 divided by 3. This is exact. I'm having a lot of problems with students not leaving their answers exact, even though I tell them to. I think it could be because students see something like this and they're like, yeah, this doesn't look good. This doesn't look finished. It's done. Like, you can't combine these. They're not like terms. So this is exact. Leave it. If I ask you to approximate it, pop it into your calculator and approximate it. I like exact. You know that. All right, let's do one application problem and we'll be done. This is going to take you back to chapter 3, section 4. All right, I'm going to give you a marginal cost function. You're like, oh my gosh, she's not talking about marginal cost. I'm talking about marginal cost. C prime of x equals 0.1230 3 x squared minus 0.12x plus 20 with fixed costs of $800. I'm going to ask you a question now based on the given marginal cost function and the fixed cost that I just gave you. A, find the total cost of the first 300 units. Now, for the marginal cost, it's just the cost to make that 301st unit. In this case, I just want the total cost of the first 300 units. So I just want C like of 300. So that's my goal. My goal is to find C of 300. So remember, the total cost is just C. Now I'm going to integrate the marginal cost here to get back to a function C. I need to find C of X before I can find C of 300. In order to do that, I'm going to integrate, and then I'm going to use the idea here of the initial value problem to then find the value of C with a fixed cost of $800. And then we'll kind of bring this back to the FTC in part B. All right, so C of X is the integral of C prime. So integral of 0.0003x squared minus 0.112x plus 20 dx. So this is going to require some calculator usage. Well, it won't require it, but you'll find it very helpful. When I increase the exponent by 1 and then I divide by the new exponent, I'm going to end up with 0.0001 x cubed. And then in this next term, I'm going to have 0.06 x squared plus 20x. Let's see. Okay, so this is my C of X. I don't know what the C is, so what I need to do in order to find the total cost function is to find C. So what I'm going to do is I'm going to use this idea of the fixed cost to determine what C would have to be. Now, the fixed cost, remember, are costs that you have to pay regardless of how many units you make or sell. So like, I mean, for instance, I have to pay the mortgage on this house whether I live here or not. So that's a fixed cost in my life. So I could live here 0 days and I still have to pay this mortgage. So the idea is if I make 0 units, I still have to pay $800. So I'm going to say that C of 0 is 800. And that comes here. C of 0 equals 800. So the cost to make 0 units is still $800. So I'm going to go ahead and evaluate this at 0. C of 0 is just C. I know, oh gosh, it's so confusing because we have C for cost and C for our constant of integration equals 800. Yikes. So that's this C. This C. This C. Okay. Equals 800. So that means C of X is 0.0001 x cubed minus 0.06 x squared plus 20x plus 800. Here's your C of X. And now you're finding the total cost for the first 300 units. So that means you're looking at C of 300, and you can put this into your calculator. I trust that you can do that, and you get $4,100. Okay, that was part A. Part B, we'll put on the next page. All right, part B, then we're out of here. Not that I'm excited about that or anything, just saying. You are excited about it, maybe. I know the videos are the most exciting part of your day. She's being facetious. Okay. I'm going to put this up in case I need to refer back to this function. E, what is the cost of the 201st through the 300th units? Mm-hmm. All right. If I'm looking at that, I can look at this 2 different ways. One of those ways is that I can think about this as just taking the cost of those first 300 units and then getting rid of the 200 units that came initially. So we could just omit the cost of the first 200 units. but then we'll also talk about sort of how this ties into your FTC and your definite integral. So if I do that, what I'd be looking for here is the cost of the first 300 units, and then we'll take away the cost of the first 200 units. And what this is going to give you is just the cost of the 201st through the 300th units. So if I do that, again, I have this cost function on the previous page. I put it up here somewhere. You could evaluate this function at 300 and then evaluate it again at 200 and subtract the difference. And if you feel like that's cumbersome, I'm going to remind you how to put this in your calculator. I'm going to go to my y equals menu, 0.0001 x cubed minus 0.06 x squared plus 20x plus 800. What's in your y equals? Go back to your home screen, variables, scroll to y variables, function, y sub 1 of 300, close your parenthesis, minus, do the same process over again, and subtract it off at 200, and you will get 900. Now, notice that this is the same thing that we would have gotten if we would have taken that integral and integrated from x equals 200 to x equals 300 of your c prime dx, because this would have eventually just given you c of 300 minus c of 200 using the FTC gets the exact same thing. Notice also, because in this case, the way that this is set up was 800 for the fixed costs that you found previously. When you subtract these two functions from each other, you end up getting the 800 to pop up here minus the 800. So that plus c ends up being negated anyway. So that's why this will work. Those fixed costs are not going to matter in this case. So you're going to be taking c of 300 minus c of 200 using the FTC to find the same quantity. Okay, that's all I have for you today. Next time, we will talk about evaluating definite integrals, which is kind of a cool section because it really just sort of tests your knowledge of like, what does this integral even mean? But we're also going to be using the FTC next time with integrals that require substitution. So if you were thinking like, wait, there was something missing from my life today, I didn't actually do any integration by substitution. Well, that's coming in 6.5. We'll be doing integration with substitution for definite integrals. And we'll be talking about changing our limits of integration from x to u, which is such an important skill. After that, we'll talk about area between curves in 6.6. And then in 6.7, we'll just have some applications for definite integrals. And that is it. We're not going to hit chapter 7 or chapter 8 in this particular semester if you're in my class. So it's not going to happen, and I'm okay with that. I hope you have a wonderful rest of your day, and I will see you next time. Good luck on your homework, and I hope you enjoy working on the FTC. Wonderful. Good times.